In 1929, a monumental shift occurred in our understanding of the cosmos. Scientists discovered that the universe is not static, but actually expanding, a realization that changed how humanity saw its place in the universe. This breakthrough came from Edwin Hubble's observations of galaxies whose light appeared redshifted, meaning they were moving away from us. Hubble's work laid the foundation for what would become the Big Bang theory, and it opened the door to a cascade of scientific discoveries throughout the 20th century. By 1957, researchers had peeled back even more layers of cosmic mystery, coming to understand that the sky wasn't just a fixed, decorative canopy. It was a living, evolving landscape filled with the forces that shape galaxies, stars, and even life itself. The elements in our bodies, from the iron coursing through our blood to the calcium in our bones, originated not on Earth but within the fiery hearts of stars. Every atom heavier than hydrogen was born in the intense nuclear fusion processes at the core of stars, and later released into space through massive stellar explosions. This cycle of creation, known as cosmic alchemy, links the lives of stars to our very own, revealing that we are quite literally made of stardust. In recent times, as technology has advanced and our observational tools have become more powerful, astronomers have focused their attention on one of the most captivating stars visible to the naked eye, Betelgeuse. This red supergiant, situated in the Orion constellation, has historically been among the brightest objects in the night sky, drawing the curiosity of both professional astronomers and stargazers alike. Yet it is Betelgeuse's recent erratic behavior that has sparked a surge of scientific interest. The star has begun to behave in an unusual manner, exhibiting significant and unexpected changes in brightness. These fluctuations, sometimes violent, have led some researchers to suspect that Betelgeuse could be entering the final stages of its life. The dramatic dimming episodes have triggered global attention, leading to intense observation campaigns by observatories across the world. Betelgeuse is far from ordinary. With a mass about 20 times greater than that of our Sun, it ranks among the largest and most luminous stars we've ever studied. Even though it appears as a faint reddish point from Earth, its actual size is astonishing. If Betelgeuse were to take the Sun's place at the center of our solar system, its outer layers would stretch beyond the orbit of Jupiter. Despite its vast scale, it lies at a relatively close distance in cosmic terms, approximately 640 light-years away. To grasp that distance, consider that even if we could travel at the speed of light, a feat far beyond what our current technology allows, the journey would still take over 600 years. With today's propulsion systems, that same trip would take millions. Even so, this immense distance doesn't reduce the significance of what's happening with Betelgeuse. On the contrary, it elevates its importance, offering us a rare, real-time opportunity to study the behavior of a massive star in its twilight years. Changes in Betelgeuse's brightness aren't entirely new to astronomers. It's long been classified as a pulsating variable star, meaning it naturally undergoes cycles of expansion and contraction that affect how much light it emits. When the star expands, it shines more brightly. When it contracts, it dims. These cycles play out over months or years. In fact, scientists have identified at least two dominant cycles, one lasting around 185 days and another spanning about 2,300 days. But what has really caught attention in recent years is the unpredictability and severity of these changes. One event in particular, dubbed the Great Dimming of early 2020, saw Betelgeuse's brightness drop to a magnitude of approximately 1.61, a significant departure from its usual state. This sudden change sparked speculation that Betelgeuse might be on the verge of a supernova explosion. The star's reddish appearance is due in part to its relatively cool surface temperature, about 3,500 Kelvin, much cooler than the Sun's, 5,500 Kelvin. Even though it's enormous, its cooler temperature means it emits less energy per square meter, which is why it appears dimmer than we might expect. The recent fluctuations in brightness are thought to stem from internal processes, particularly the fusion reactions occurring in its outer helium shell. As Betelgeuse nears the end of its life, it transitions from fusing hydrogen to heavier elements like helium, carbon, and oxygen. These nuclear reactions send waves of energy through the star's outer layers, causing it to expand, shed mass, and generate powerful stellar winds. These outflows, combined with pulsation cycles, create a kind of rhythm in the star's light, what scientists sometimes refer to as the star's heartbeat. To understand these phenomena, astronomers use a variety of tools. Photometry helps track brightness changes over time, while spectroscopy breaks down light into its components, revealing vital information like surface temperature, elemental composition, and how fast parts of the star are moving toward or away from us. In recent years, advanced computer models have become essential in this research. These simulations incorporate complex equations related to stellar structure and nuclear reactions, helping scientists visualize and predict what might be happening beneath the star's surface. One significant factor behind Betelgeuse's unpredictable behavior is convection, a process where hot material from deep inside the star rises while cooler material sinks. These massive convective currents can be larger than Earth itself, and they play a key role in how energy is transported to the surface. Variations in these currents, or changes in the efficiency of this heat transport, can lead to noticeable shifts in brightness. In some cases, material ejected from the star can form dust clouds that temporarily obscure its light, creating a dimming effect that doesn't reflect an actual drop in brightness. Although Betelgeuse is generally thought to be a solitary star, scientists haven't ruled out the possibility of it having a hidden companion. In binary systems, stars orbit each other and can exchange mass, dramatically altering how they evolve. Such interactions can disrupt a star's internal balance and trigger changes in brightness or fusion activity. While no solid evidence for a companion star has yet been found, the theory remains on the table as researchers continue exploring all possible explanations for Betelgeuse's behavior. The most dramatic scenario, and the one that captures public imagination, is that Betelgeuse is nearing the end of its life and could soon explode in a spectacular supernova. Like all massive stars, Betelgeuse maintains a delicate balance between the outward pressure of fusion and the inward pull of gravity. But this balance can't last forever. As the star burns through lighter elements, it eventually begins fusing, heavier ones culminating in the creation of iron. At this point, fusion no longer generates energy. Without that outward pressure, gravity takes over and the core collapses in a matter of seconds. This collapse triggers a violent supernova, ejecting the star's outer layers into space and releasing a burst of light and energy on an almost unimaginable scale. If Betelgeuse were to go supernova, it would be a celestial event of extraordinary magnitude. Its explosion would be so bright that it could be seen during the daytime for weeks or even months. It would temporarily rival the brightness of the full moon and become the most luminous object in the sky. Fortunately, Betelgeuse is far enough from Earth that even a powerful supernova wouldn't pose a threat to our planet. But if such an event were to happen closer to home, the results could be devastating. Gamma-ray bursts, sometimes linked with certain supernovae, could strip away Earth's ozone layer, leading to harmful levels of ultraviolet radiation. This could endanger human health, disrupt ecosystems, and negatively impact agriculture. Additionally, the electromagnetic pulse from a nearby explosion could interfere with satellites and electronic systems. After the explosion, the collapsed core of Betelgeuse would leave behind a remnant, either a neutron star or, if the mass is sufficient, a black hole. A black hole formed at a distance of 640 light-years would pose no danger to Earth, but it would offer a valuable chance to study some of the most extreme conditions in the universe. These objects emit intense radiation as material spirals into them, giving scientists a unique laboratory for studying high-energy astrophysics and the nature of gravity. No matter what the outcome, Betelgeuse's fate will mark the end of one stellar life and the beginning of a new era in our understanding of the universe. The eventual death of this giant star will serve as a powerful reminder of how stars live, evolve, and die, and how their life cycles are essential for cosmic evolution. Supernovae are not just dramatic endings, they are also crucial beginnings. They distribute the heavy elements created in their cores into the surrounding interstellar medium. enriching gas clouds that will one day birth new stars and planets. In this cosmic cycle of death and rebirth, the explosion of one star paves the way for the creation of many others. Should Betelgeuse go supernova in our lifetime, it would be a rare and extraordinary event, an unforgettable display of celestial power, and a vivid demonstration of the universe's ever-changing nature.